CIS 250 data.
Okay, so we're now back in the data structures book, and again, we're not going to get into any of the Java. We're going to stay more at the formula or conceptual level. So there on page 202, the first thing it talks about is a stack. Now, a stack is, I want you to think of a stack is, it's a tubular thing, and we're going to, each one of these little sections, if you look right here, we've got this little oval shaped thing. Think of that as a bunch of data. It's an object that holds data, and so I'm going to put them inside of this tube. Now it's a Pringles can, so I'm going to load it with potato chips. So each chip I put into the Pringles tube is data. Okay, it could be a record for employees, it could be a record for our movie database, whatever the case may be. So it allows us to basically put that information in there. Now, in this particular case, the example they're using is a Pez dispenser. Now, the Pez dispenser has what is called a LIFO principle. And what that means is the last one put in will be the first one we take out. So this guy right here that's closest to the spring was the very first one you put in. Now there's no other way to get that out except taking the newer ones out. So it's called LIFO, or LIFO, or last in, first out. So the last one in will be the first one we take out. So this piece of candy in our Pez dispenser was the last one we put in, and when we tilt the head up, it's to be the first one we take out. So when we have those types of situations, again, when we put data in, the only way to get it back out is via the LIFO. Okay, so we use the stack abstract data type to do that, and we have some different commands that we use to basically put items in there. We have what is called the push. So I can say push some object. So E is going to be the object. So I say push E. It's going to then put that Pez candy in the Pez dispenser. Pop says I'm going to tilt the head up and take it out. So so what's going to be the thing that comes out when we do a pop? It's going to be that very first candy, the last candy we put in there. So if this were a food product, this is the very wrong way to do it. We always want to make sure that we, again, if you're going to McDonald's, they've got those big trays of hamburgers. The oldest ones are in the front and the newest ones are in the back. Well, we wouldn't want to do just the opposite. We wouldn't want to put the new ones up front and the oldest ones in the back, because then we got that old data will never ever, I should say, those old burgers will never, more than likely, take a long time to get sold. No, we want the very next one to be sold be the oldest one. I can get a size, so size will tell me how many objects are in the stack. I've got an isEmpty command. I can say if isEmpty. It's a Boolean switch. And it says if that particular tube of data is empty, it will come back true. If it's not, it will come back false. Top, I can say always give me the top. Okay, again, pop says pull the candy out, or pull the data out, and now it's out of the stack. Top says just tell me what's there. Okay, so it's kind of a nice way to say what candy is there. Is that strawberry? Is it lemon? We can kind of tilt the head up and look and say, oh, it's strawberry. So I just looked at it. I didn't remove it, but it's still sitting there. On this page 203, it kind of shows a succession of commands that are used. So I say push 5. So now what's in the stack? 5. I say push the number 3. So now it's got 5, 3. I say now pop. What's it going to do? It's going to pop the last one, which is 3, so it pulls the 3 out. I say push 7. So now it's got 5 and 7. I say pop. It grabs 7, so what's left is 5. When I say top, it just lets us look at the 5. We can see it, but it's still in the stack. If I say pop, it brings the 5 out. 5 is now gone. If I say pop again, it's going to error out because it'll say you've got nothing in the stack. Okay, you done popped them all out. I can say isEmpty. It's going to be set to true because yes, it's true. So I should have done the isEmpty before I did this pop and got the error. I can say if not is empty, do a pop. Okay. Then I say push 9, puts in a 9, push 7, puts in a 7, push 3, puts in a 3, pushes in 5, pushes, and then I can say what's the size? Well, it's got 9, 7, 3, and 5. Again, 5 being the oldest, 9 being the newest. So to pull them back out, I got to pull them out from the right side. So now I say pop, it brings out the 5. Now I got 9, 7, 3 left. I push in an 8. I do a pop, it takes out the 8. I do a pop, it pulls out the 3, and what's left is 9 and 7. Again, 9 is the oldest one. It's going to be the last one to come out. Again, we can kind of see some of the different Java commands on how they would be used. I don't want to get into that. Yeah, there's more code there. This is kind of a cool little code. It will basically take in an HTML file and basically remove all of the tags. So it basically says, so it strips the first and last characters off a tag. So what is a tag? A tag is anything that's in a less than or greater than symbol. So what this little code will do is it goes through and it says, oh, you're a less than. I'm going to look for a greater than sign. I'm going to remove everything in between, and it just keeps doing that. And when the output will be is this nice little thing right here that shows the little boat, tells a story, and then it basically talks about the 3 points of the story. Where over here is the actual HTML document. So again, kind of a cool way to use the stack. So it basically uses every single character is an object in a stack. So it brings them all in, and then it basically looks for them, and then basically looks for a less than. Once it finds a less than, it keeps going through the stack till it finds a greater than, and basically pops them all out. Okay. Okay, so now we've got queues. Okay, so that was a stack. So stacks basically are LIFO. Last one in is first one out. Queues, on the other hand, are what we call FIFO. So think of a Pringles can where we open the top, but we also can open the bottom. So when I put a potato chip in, it goes all the way to the bottom of the tube, and I keep loading more chips in. Now this time I'm going to grab from the bottom, so when I grab the chip, it's grabbing the oldest. So now we go to McDonald's and we see those sandwiches in order. This is a queue. Okay, now a queue, if you've ever been one of those lines at Six Flags or Disney World, whatever the case may be, where they've got the velvet ropes, that is called a queue. You're going through a queue and you're going around and basically until you get to the end. So the first person in that queue is the first person out the other side. The term queue comes, it's an English term. If you actually go over to England, you actually hear the term queue when you're, we call it getting into line. Over there they call it getting into a queue. So we have NQ and DQ. So an NQ says insert an element at the rear of the cube. So basically puts it in at the beginning. DQ says remove and return the object from the front. So NQ, it says go into the line. So I'm at Six Flags. I just walked into the velvet ropes or the chains, whatever they happen to have. I just walked in, so I just did an NQ. I'm walking all the way through. I get to the other side. The guy walks up and says, okay, your turn to get on the roller coaster. He just did a DQ. He pulled the first person out, which was me, and put me on the roller coaster. We have the same size. We have the same method size, tells us how many items are in that queue. We have is empty. We can actually determine whether that queue is empty or not. And then we have front. That's like top, except top shows the last one in, It doesn't remove it, it just looks at it. Front says, hey, tell me what is in the front. Don't pull it out of the line, don't DQ it. Just tell me what it is. I want to know what it is, so we can kind of see what data is waiting to come out the other end. I'm not going to go through this, but you can kind of go through this yourself. So we got NQ, again, it puts it in. NQ, DQ, NQ, DQ, front, DQ. So again, kind of the same sort of thing that we had available to us with a stack. So with the stack, again, it only goes in one way and it can only come out one way. With the queue, it only goes in one way and it comes out the other end. Like, we can't basically do anything but that. With the DQ, DQ says we can pull from either end. I can put them in this way, or I can put them in this way. I can pull from this side, or I can pull from that side. So that's the great thing about a DQ. So we've got add first, so that puts it at the beginning. Add last, that puts it on the back side. So it's kind of like if you ever went to Six Flags again, if so you saw somebody in a wheelchair, they were kind of pushed through the back of the line and they went into the front of the line, so that was add last. So they basically put it in at the end. I can remove first, so it means remove somebody at the end of the line, or I can remove last, it means basically pull somebody out of the line who's basically pulling on the other side. I can get first, I can get last, I've got size, I've got is empty. So again, a lot of different methods available to us for a DQ. So a DQ, I can put things in either end. Okay, there is no such thing as last in, first out, or first in, first out. It doesn't matter with the DQ. I can put them in either side. I can pull them out either side. Doesn't matter. Okay, but remember, with any kind of a queue, whether it's a stack, a queue, or a DQ, I cannot pull from the middle. Okay, because again, those things are inside of it, so think of them as being inside of a tube. If I need to get to that middle object, I have to pull out from this side first. Okay, so you can kind of look at some of those at your leisure and kind of read those. So the next item we're going to talk about is a thing called a tree. So a tree, again, is another way to organize and relate data together. Okay, and a good example of a tree is a genealogy tree. So you've got your grandfather and your grandmother, and then basically from there you have your mom, and then from your mom you have your siblings, and it kind of goes on from there. So very, very important in a data structure world, and that's basically putting things into a tree view. Okay, so here we have I don't know what they're doing here, but some kind of a, oh, it's a family tree. They're showing Abraham, and here's all of the sons and daughters, and looks like these two sons or daughters had no kids. This one had 5 kids, this one had 2, this one had none, this one had a whole bunch, and this child had 2 children of their own, and then each one of those children had a bunch of children. So we are going to be talking in a parent-child relationship. We're going to be dealing with that a lot within the data structures. We talk about trees. So if we look here on page 285, here we've got electronic RS. So this is a store. Inside that store we've got R&D, we've got sales, we've got purchasing, we've got manufacturing. R&D and purchasing, that's all they've got. There are no other departments inside of that. Manufacturing, we've got a TV department, we've got the CD department, we've got the tuner department. In sales, we have domestic, we have international. Domestic stops right there. There's no other departments inside of that. But international, we have got a Canadian, South America, and overseas. And overseas, we talk about the 4 different countries there, and it stops. So again, for us to get from electronics RS down here to Australia, I have to go to sales, I have to go to international, I have to go overseas, then I even have to go to Australia. And again, same terminologies we would in genealogy. Here we have a parent, here we have a child. And here we have 3 children under this parent, and these 3 are called siblings. They are siblings. So then we got these things called an edge and a path. Okay, so an edge is going to be a pair of nodes. So we come down here, we've got the edge, which is basically these two guys. So these two guys basically fall underneath an edge situation. So the parent edge of a tree is a pair of nodes such as that, U and V. So, where's their examples? Is that down over here? Anyways, a path is basically how we get from a grandparent down to a grandchild. So we have to go through grandparent to child. That's called a path. We have ordered trees, which are basically linear ordering for children. So we basically, again, if we look here, we've got a book. We've got a preface. We've got part A, part B. We've got references. And within part A, we've got chapter 1 and chapter... we got chapter 1, which has 1.1, 1.4. We got chapter 5. So again, we've got part A, chapter 1 through 5. These are ordered, okay? So chapter 1, chapter 2, chapter 3, chapter 4, chapter 5. Here's some of the different methods we would use in Java. I've got an element. I've got my root. Now, what is my root? Well, if we look at our tree, in this particular case, book can go no further up, so book is the root. We start with root book and come down, so book is the root of our tree. Our parent and child, so there we have our parent and child situation. Hold on. So over here on page 286, it talks about internal and external. An external node is one that has no children. So if we look here, grades is external. An internal node is one that has children. So external, no children. Internal, has children. So if we come over here, again, we've got is internal, is external. We can check to see if that statement is true. We can say, is that node an external? If it's true, that means it has no children. If it's not true, that means it is internal and it has children. Is root, I can say is book root, and it will come back true. Size is empty. No, I don't worry about iterator or replace, but just realize those are different things we can do. So here's our implementation of a tree. Again, you can kind of look at that at your leisure. Not expecting to code that, but you should be able to kind of go through there and somewhat understand what is going on. So how do we traverse through this tree? Again, I have to go from my parent to a child to a grandchild. I can't go directly from a parent to a grandchild. I have to go through the parent to basically get there. So again, when we talk about tree traverse, we're traveling through a tree, we can talk about depth and height. Okay, the depth is the number of ancestors, how many times we have to go down, and the height is, I always get those two. A height of a node is defined recursively. If V is external node, then the height of V is 0. So if I look, so again, think of a height. I'm starting with a child. How many children and grandchildren do we have from there? So when I look at depth, I'm talking about the whole thing. How many basically levels do we have down? That's everything. Height, I'm going to start with just one node, and I'm only going to look down. So I'm only looking at internal nodes. Only internal nodes have height. If an internal node has a height of 0, that means it is an external node. So here we have a post-orbital travel. So if I were basically going through this in code, I would start here with paper, and I would come down to title. Since title is an external node, it would automatically jump over to, so if I'm trying to go through this guy one node at a time. So this is how it would work. It would go to title, we'd go over to abstract. Well, since abstract doesn't have any children either, it's external, it would look at the next, it would look at its sibling and say, do you have any children? And it would go to the children and say, do you have any children? You don't, then it would start with that child. Then the next item would be its sibling, or first it would check to see if any children. Since it doesn't have any children, it goes to the next node, the sibling, checks to see if it has any children. Since it doesn't, then the next place it goes is its parent. Then that parent goes to the next sibling and says, do you have any children? You do. It starts there. Again, it would check, do you have any children? And you can see how it's kind of going through this. It comes back around. So that's called a post-order traversal, how it travels through the node. I'm sorry, through the tree. Binary trees have basically always have two. A node will always have two children. Think of those children as yes or no. So here we have a question. Are you nervous? Yes. Savings account? No. Will you need to access the rest of your money within the 5 years? So anyways, it kind of goes through yes or no question situation. Binary means two. So in this case, yes or no. Here's another example of a binary tree. Start down here and I want to do a plus. Okay, I'm going to do an addition. What am I going to add? I'm going to add this child and this child. Well, this child is an X. That means multiplication. What's it going to multiply? It's going to multiply the number 3 and this child. Well, what's this child? It's a subtraction. So I've got 7 minus 4, which is 3. So we'll multiply 3 times 3. And now I have 9 here. I add 9 and 6 together, and that gives me 15. And we kind of do the same thing over here. That's division, there's multiplication, addition, so on and so forth. So this is basically an arithmetic operation with a binary tree. Okay, so I think that's what we'll cover for now. When we come back, we'll continue on with some more of the data structures and basically continue on this lecture.